Hi, I'm Swapno, and this is the fifth video of the Feynman Path-Integral series. So today we'll continue with our discussion on variational calculus. Okay. So last time I showed that a straight line is the shortest path between 2 points. Okay, but the proof was indirect. Okay, so there we assumed that we know that the shortest path is a straight line. Okay, and then we considered slight variations. Okay, about the straight line, right, and showed that the length didn't change, up to the first order of variation, okay, about the straight line. Today, I will not assume that I know that straight line is the shortest path, okay. What I'll do is that I'll use the stationary principle, okay, which is that, the first order variation about the optimal path is 0, okay. And using that principle and the length functional, I'll derive, a differential equation, okay, solving which I will get a straight line. Okay, so that is actually more along the conventional lines of doing variational calculus. Okay, so you always, using the variational principle, you get a differential equation, and solving which you get your optimal curve. All right, so let's get started. So the length functional is given by this expression, xa to xb, right? So basically, this is x and this is y. Sorry, this is the point A and this is B. So let's imagine you have a curve between A and B, and the length of that curve is given by, this integral. Okay. So what I'm going to do is that, so this is a functional because this depends, its value depends on the function, on the whole function, entire function defined in between these two endpoints, x and xb. All right. Okay. So what I'm going to do is that I'm going to consider variation of L, okay, which I'll write as delta L, okay. Okay, before that, let me just say a few words about the notations I'm going to use, okay. So I'll assume that there is an optimal path. I don't know what that is, but there is one, okay. So let's say this is the optimal path, okay, the path for which the length is a minimum. I don't know what that is, so I didn't draw it as a straight line, okay. So, and then I'll consider variations about that line, right? An arbitrary, small but arbitrary variation about that optimal line, okay? So, all right? And this variation I'm going to denote by delta yx. So if yx is the optimal curve, then delta yx is the variation, okay? So the new curve is given by yx plus delta yx, okay? So this is, and sometimes I will write this as yx goes to yx plus delta yx. All right. So now a couple of things. I mean, by the way, so in the book, in the Path-Integral, with basic calculus book, you will not see this notation as far as I remember. I think I used eta, okay, for delta yx because I just didn't want to introduce unnecessary jargons and new notations, in that book. But today, in this video, I'm going to use, I'm not going to use eta x, I'm going to use this delta y symbol because this is what you will find mostly in literature on path integral, okay, or on variational calculus, all right. So, okay, so delta means really the variation. It's really this, this small variation about the optimal value, okay? It's a change, that's why we're using delta, all right? Okay, so when yx goes to yx plus delta yx, what happens to dy dx squared? Okay, which is a term inside that, okay? So let's actually see how much this one changes, all right? So our yx goes to yx plus delta yx. Oops, right? So dy dx is going to what? dy dx plus d dx of delta yx, right? So what you can do is that you can square both sides. So, dy dx squared is going to go to dy dx plus d dx of delta yx squared. And you can expand this, which would give you dy dx squared plus 2 dy dx d dx of delta yx, right? I mean, do you see that? And there's a third term, which is the square of this term, but I'm going to ignore that, okay? Because that is too small, Okay, that is the second order term. You see, this is a, this is b, a plus b whole squared is a squared plus 2ab, and then there's a b squared. I just ignored that because that is a second order term in, involving the change delta, okay? All right, so you see, dy dx squared goes to dy dx squared plus that, right? So the change delta of dy dx squared is, up to the first order, is d 2 dy dx, then d dx of delta yx. Okay, do you see that? Okay, so the change is all right. So change is given by just this expression. Okay, you will be needing this result. Okay, when we vary delta L. Okay, when we vary L. So our goal is actually to understand how much L changes, how much the functional changes when yx is changed by an amount of delta x, right? Let's actually do that. So this is, we'll need this result, okay? So maybe we can just write it here, okay? Delta dy dx squared is equal to 2 dy dx times d dx of delta y. I'll just write delta y, okay, instead of delta yx. Now notice something interesting. This delta, okay, this delta is just like a d operator, right? I mean, if you just imagine this is u squared, how do you write du squared? It's 2u du, right? So one thing I'd like to emphasize is that, this d and delta, they kind of interchangeable, they're independent, they don't talk to each other, okay? These are two different kinds of variations, right? So you can always interchange them. So let's actually use this, okay? Let's say that, just like you have this relationship involving d, you can also write delta u square as 2u delta u, okay? And let's say u is dy dx, all right? Okay? So if this is, I'm trying to check if this is true, okay? So let's see what you get, okay? On the right side, we'll have 2 dy dx, and then delta u, right? U is dy dx, okay? Which is 2 dy dx, and then d, but you see, the point that I'm trying to make is, okay? This, what you got here, okay? Using this rule is slightly different from what you have up there. Do you see the difference? The difference is in the position of d. See, you have d dx is, it's kind of like d and delta have been interchanged, but they are actually the same, because remember what I told you, like d and delta, they are independent, okay? They're two different types of change, so they're exactly the same. So whenever, if you ever see an expression like this, feel free to write it this way, okay? Take the delta inside, just swap d and delta, okay? And you'll get that, okay? So the bottom line is, this result holds for this delta, operator or notation or whatever you want to call it as. All right, okay. So now we have that result, and I'm going to erase everything else, okay? Oh, by the way, one other thing is, I should have mentioned, the delta y are actually 0 at the two endpoints, okay? Because the variations are 0, right? You can see that, you're considering curves which share the same endpoints. So that means we can write delta yxa equal to 0 and delta yxb equal to 0, okay? This has to, okay, we'll need those two. Okay, anyway, so let me just erase everything. Okay, so enough of introductions and, setting the stage, right? So let's now vary delta L, and this is going to be a really fun part. So see, it's just like, the chain rules and, the product rules, whatever you did in calculus, okay? So delta L means you can take delta, the change, inside the integral. So I'll write this as delta 1 plus dy dx squared dx, okay? Now I'm going to focus on just this part, okay? And I'm going to treat delta just like, the d operator, okay? Although they're not the same, but the mathematics is the same, right? So I'm going to do that. So this is like, I'm going to use now chain rule, okay? So d u to the half, okay, where u is just this part, let me write this down here. U is defined as 1 plus dy dx squared, all right? So d u to the half is what? Is equal to half u to the minus half du, right? The chain rule, right? So, and then this is going to be half, e to the minus half is 1 over square root of u, which is 1 over square root of 1 plus this thing, right? And then you have delta u, okay? Now this is going to be interesting. The delta u is delta of a constant plus delta of that, okay? Delta of a constant is 0, right? The change, just like in calculus, okay? The derivative of a constant is 0, d of a constant is 0, this is delta of a constant, which is also 0. And then you have delta of that thing. And guess what? We have already found this here, okay? So this is 2 dy dx, and then you have d dx of delta y. All right? So instead of delta u, I'm going to write that, okay? That expression. So it's 2 times dy dx, and then you have d dx of delta y, right? So 2 cancels out, and then you have a dy dx multiplying this expression involving dy dx, and then you have delta y, okay? So that's your delta L, and you have a dx. Everything is happening under the integral sign, right? So, okay, so you still have an integral. So we write it here, okay? So delta L is xa to xb, all right? This expression, so let me write dx first, and then I have dy dx in the numerator and square root of 1 plus dy dx squared. Let's see. And then d dx of delta y. Okay, that's my change. This is the L. Okay, this is the delta L. Okay, do you see that? Okay. Next, what I'm going to do, I'm going to use integration by parts. Okay, on this expression. All right. I hope this is not. Let me just put a kind of a divider. Okay, that is it. I want to still keep. I thought I erased this, but let me just keep that expression. So this is L and this is delta L. Okay. So now I'm going to use integration by parts. Okay, which is what? You know what? Let me just erase everything else because I think you got. You got the rest of the mathematics, and I need some board space. Okay. All right. So this is delta L. Okay. This is what you got from L. Okay, from the length functional. And the idea is to set this to 0, right? That's the that's the variational principle. That's the stationary principle. I said, okay, that if you have found the optimal path, then the variation, first order variation about that path is going to be 0. Okay. Before we can set this to 0, we need to massage this expression a little bit, okay? So we will use, okay, the integration by parts, which is integral, I don't know exactly what your favorite version of integral by parts is, but I remember it this way, okay? Like u dv is equal to uv, okay, at xa to xb, minus integral v du, okay? U and v are functions of x, okay? All right, so in this case, I'll take this as u and this thing as, this with dx is dv. Okay, so let me just write this dx here, this is dv. Okay, so this is uv minus v du. Okay, so now you see u is just this part, like this sort of beastly looking expression. It's not actually as bad as it looks, but it's as you'll see. Let me write this down. So dy dx divided by this 1 plus dy dx squared, and then v is just okay. So what is v? Okay, dv is this thing, right? This whole thing. You see, d dx of delta y dx, right? That whole thing is dv. So what is v? So you get from here, you get v is equal to delta y, right? You just integrate this derivative, so you get the main function dy. Okay, so v is just dy. And I'm going to evaluate this between x and xb, and then minus, I'll need that v again, right? So v is dy, right? And then du, right? Du is you're taking the differential of this, so which is d dx of this whole thing, dy dx divided by square root of 1 plus dy dx squared, and dx. Right? That's du. If this is u, then the du is the derivative of that and then dx, right? It's happening between x and xb. Now the good part is that, dy vanishes at the two endpoints, x and xb. Remember, like all the paths have the same endpoint, so no variations, okay, at the two endpoints, okay. So dy here, okay, dy xb, I mean delta y xb is equal to 0, delta y xa equal to 0, right? So this term vanishes, this goes to 0. So you're left with just that, okay? And that is what? This expression is what? This is delta L, right? This is delta L, okay? Now this is 0 for any arbitrary variation of delta y, right? Remember, delta y is completely arbitrary, except for the fact it's small and, it's 0 at the two endpoints, right? Because it's arbitrary, this part has to be 0, okay? Otherwise, delta L wouldn't have been 0, right? For any arbitrary function, you can't have 0, okay? I mean, unless the integrand itself is 0, all right, okay? So we set this to 0, okay? Now what does that mean? If this is 0, then it means the function inside is a constant, right? ddx of a constant is 0. So let's write that down. Okay, so I'll just erase the integration by parts and write the integrand equal to 0, that equation here. So dy dx divided by square root of this thing is equal to a constant, okay, which is the same thing as saying, ddx of this is 0, right? Okay. Now you can, do cross multiplication and so on, and you can solve for dy dx, and you'll see that dy dx turns out to be another constant m. Okay, m is a function of c. Okay, you can just do cross multiplication, okay, and solve for dy dx, okay, which is a constant, which should turn out to be a constant involving c. Okay, I don't know c, so there is no reason to kind of write the constant in terms of c. So I give it a new name. I call it m. Okay. Now dy dx equal to m. Okay. I mean, what is the solution to this differential equation? This is one of the simplest, okay, differential equations, right? So the solution is y equal to mx plus b or mx plus c, whatever you want to call it as. Okay, which is the equation of a straight line. Okay. So you see, by using variational calculus, we showed that the length functional, okay, is minimum, okay, when when the function is a straight line, right? And we actually considered variations about what is supposed to be the optimal solution, and we set that variation to 0, and then solved the differential equation, which gave us the equation of a straight line. Okay, so this is the more direct proof. Okay. We didn't know, right, beforehand that it would come out as a straight line, okay? But we proved, okay, we found that it is a straight line, okay? I mean, solving the equation, we got a straight line, okay? All right, so anyway, so let's see, what else? Right, so, this is a general equation of a straight line. So let's, just write the specific form of the straight line for our problem, right? So remember, the line, we are considering lines passing through 2 points, right? With coordinates xa, ya, and xb, yb, right? So the slope between these 2 points, if we know that it's a straight line, okay, we can find the slope, which is yb minus ya divided by xb minus xa, okay? And we can use the Point-Slope form, okay? So y minus ya is equal to m, which is this, yb minus ya divided by xb minus xa times x minus xa, right? This is called the Point-Slope form of a straight line, okay? So this is the equation of a straight line that passes through, 2 given points, and this is the shortest distance. This gives us shortest distance between the 2 points, okay? Okay, thank you for watching the video. I hope you enjoyed today's session. So in the next session, we will be seeing more examples of variational calculus. Okay, so today we talked about the length functional, and in the next session, next couple of sessions, we'll be talking about other functionals. Okay, functionals which are important in path integrals and in physics in general. Thank you.